The word chirality comes from the Greek word for hand, and it can be thought of as a molecular handedness. The technical criteria for chirality is anything that is not superimposable on itself. Chiral objects have no plane of symmetry, and their mirror images are not superimposable. So what does this mean? We actually have quite a bit of experience with chirality because our hands and feet are chiral. If we consider our hands or gloves, there is no plane of symmetry on each hand. If I draw a line down the center of a glove, each side is different. One side has a thumb, the other side has a pinky. If I take the left glove and put it on top of or superimpose it on the right glove, they won't be the same. The thumbs will be on opposite sides. So hands, gloves, shoes, and feet have mirror images that are not superimposable, and therefore they are chiral. We know that a left shoe doesn't fit properly on a right foot. Molecules can be handed or chiral also. Chiral molecules have what are known as chiral centers. Chiral centers are tetrahedral carbons bonded to 4 different substituents. So we don't need a mirror to determine if a carbon is chiral. We just need to figure out if it is bonded to 4 different substituents. Non-superimposable mirror images are known as enantiomers. If gloves were molecules, they would be enantiomers. Enantiomers have the same boiling point, melting point, color, and chemical reactivity. However, enantiomers react differently to polarized light, and they interact differently with other chiral molecules. To determine whether a carbon is chiral or not, we have to determine whether it has 4 different substituents. The carbon on this slide has 4 different substituents: fluorine, hydrogen, bromine, and chlorine. So it is chiral. Sometimes it's a bit more work to determine if a carbon is chiral or not. Let's consider 2-butanol, which has a hydroxyl group bonded to the 2-carbon. The first carbon has 3 hydrogen atoms bonded to it, so it is not chiral. The second carbon is bonded to 1 hydrogen atom, 1 hydroxyl group, 1 methyl group, and 1 ethyl group. When we consider chirality, we can't just look at the bonding to 1 atom. We have to consider the entire substituent bonded to the carbon in question. Since carbon 2 is bonded to 4 different substituents, it is chiral. Carbon 3 and 4 are not chiral since they are each bonded to more than 1 hydrogen atom. To identify chiral carbons, first, locate the tetrahedral carbons in a molecule. Next, determine if there are 4 different substituents on any of the tetrahedral carbons. If so, it is a chiral center. Chiral centers are often identified by asterisks.